arc length. Okay, so let y equals f of x be a curve in R2. Okay, R2 is the Cartesian plane. The arc length of the curve. Okay, or the actually just the length of the curve from x equals a to x equals b is given by, so there's a formula for this. Length will be the integral from a to b of the square root of 1 plus f prime of x squared dx. Okay, this is the formula to calculate the arc length of a curve. Okay, the length of a curve over an interval. Okay, well, I'm going to explain you where this formula comes from. But first, let's do at least one example to understand how this formula works. Okay, so example, and then we're gonna prove it. Find the length of the curve find an example. Y equals x cubed over 6 plus 1 over 2x on the interval, let's say 1, 2. Okay, so that's the question. Okay, so just for you to see, to visualize what's happening here, I have a function, or I don't know, a curve. In this case, it's a function. And I don't know how it goes, but I'm interested in from 1 to 2, I need to find the length here. I want the length of this curve. This is what I'm looking for. Okay, that's L. Okay, so that's what we're doing now is we're just, we found a new operator, which is the integral, the definite integral, and so now we're just finding what we could use it for. So we use it for area between curves. Oh, that's nice. We could use it for areas. We could use it for volumes. We could use it for arc length. You'll see there's many things we could do. After this, I'm going to show you how to solve differential equations, average value of a function. Okay, you'll see. So let's do this. Okay, so the first step. So I need to find what am I going to integrate? Okay, so f of x is this function. So let's go. F of x is x cubed over 6 plus 1 over 2x. Let's find f prime, because I'm going to need f prime here. So f prime, the derivative is x2 over 2 minus 1 over 2x2. Okay, you with me? Yeah, I just did the derivative. Then I need to square it. So let's find it squared, what it is. F prime of x squared. Okay, so let's square this. So I get x4 over 4 minus 2ab. So I get minus 1/2 plus b2. So 1 over 4x4. And then I'm going to add 1 to it. So let's see. So slowly I'm building the inside of the roots. So if I add 1 to this, I get the same thing, but it's plus 1/2. x4 over 4 plus 1/2 plus 1 over 4x4. And this is exactly, so if you square this, you get that. So if instead of being a plus or minus, it was a plus, this would have been a plus as well. So this is the same thing as just x2 over 2 plus 1 over 2x2 squared. Okay, if you factor this, you get that. Okay, so this is perfect because that's what's going to be in my square root, and it's a perfect square. So when I'm going to do the square root of this, I'm just going to get rid of the root. Okay, so I'm sort of running out of space.
Sir?
Yeah.
Please, could you re-explain why the minus sign changed into plus?
Oh, this plus here?
Yeah.
Because I added 1 to it. See?
Oh, okay.
You add 1. So 1 minus 1/2 becomes plus 1/2. Get it?
Okay, thank you.
Okay, and so from here, let's see if I could fit it here. And the worst case, I'm going to continue down here after. So the length is the integral from 1 until 2, right? From a to b. So from 1 to 2 in this case. Of the square root of, so the square root of 1 plus f prime of x squared. So it's just x2 over 2 plus 1 over 2x2. That's it. And dx. Okay, and this is a very easy integral for us. You can still see, yes. Okay, so let me try, I think I could fit it here. So the antiderivative of this is x3 over 6. Minus 1 over 2x. I think that's what it is. And then all this evaluated from 1 until 2. And I don't know what I get. I need my calculator. Or I could do it mentally. 8 over 6 minus 1/4. I don't know, I'm just going to calculate it. So 8 over 6 minus 1/4. And then minus 1 over 6 and plus 1/2. So I get 17 over 12. Okay, so r squared. Okay, so r is the real numbers, the real line, the real number line.
Yeah.
Okay, that's the real number line. R squared, it's called the Cartesian product. It's a multiplication of two sets. Okay, and how do you multiply two sets? Well, you find all couples. This is R2. So So it becomes a plane.
Okay, okay.
R3, which we'll do in linear algebra in Cal 3, it's of course now the three-dimensional space, which is all, so it's R here, R, and R. It's the set of all triples. So here, a point here is X, here a point is now XY, and here a point is now XYZ.
Okay, so that's the symbol.
Yeah, that's simple. R, R2, R3. So you could do also do R4, R5, R, N, any size. Okay, so
Okay.
in linear
I
algebra,
thought it was like L or.
no, it's R. It's R, but we use it as symbol. We write it like this to show that it's a mathematical term. Okay, like
Okay.
you've done this. You've done this set N. You've done N, and you've done Z. No, in high school, you've done this. No.
No.
Q. You haven't done this?
No, sir.
Oh, wait. Okay. Example. Find the arc length of, so f of x equals x2 minus 1 over 8 ln x on 1, 2. So right away, f prime is 2x minus 1 over 8x. F prime squared is 4x2 minus 1/2 plus 1 over 64x2. Is that what you got? 1 plus f prime of x squared. So you add 1 to this. Again, this minus 1/2 becomes plus 1/2. So 4x2 plus 1/2 plus 64 over x2. And that is exactly equal to 2x plus 1 over 8x squared. Okay, so this is a perfect square. Just like this was a perfect square, this is a perfect square. Length, integral from 1 to 2 of, so the square root of this, so 2x plus 1 over 8x dx, and this is x2 plus 1 over 8 ln x, evaluated from 1 to 2. Okay, and so if you plug in 2 here, you get, so 4 plus 1 over 8 ln of 2 minus 1 plus 1 over 8 ln of 1, which you all know that this is 0. And so my answer is 3 plus 1 over 8 ln 2. This is your arc length. So find the arc length of f of x is equal to the square root of 4 minus x2 on interval -2, 2. So as usual, we find f prime. So this will be negative x over the square root of 4 minus x2. Okay, that's the derivative. If we square this, I get x2 over 4 minus x2. And if you add 1 to it, you will get 1 plus x2 over 4 minus x2. And if you simplify this, you get 4 over 4 minus x2. Okay, and so the length will be the integral from negative 2 to 2 of the square root of that. So 2 over the square root 4 minus x2 dx. So far so good? So how do we solve this integral now? Anybody?
By parts?
No, not by parts.
Trig substitution.
Trig substitution, okay? A2 minus U2. So you use trig substitution. So I don't know who asked me, is the test going to be on everything since the beginning of the year? So obviously, see, I could ask you a question on arc length, or you have to do a trig sub. Could happen. Okay, so x will be here 2 sine theta, dx is 2 cos theta d theta. Let's replace. So equals 2. The integrals, obviously I'm not putting the bounds yet. 2 over the square root of 4 minus 4 sine squared theta times dx, which is 2 cos theta d theta. And now I'm going to take care of the bounds right away. Right here. So if x is negative 2 and if x is 2, what is theta? So if x is negative 2, if x is negative 2, then sine of theta will be equal to negative 1. Okay, so negative 1. So when is the sine equal to negative 1? When we're at negative pi over 2. And if x is 2, so the sine of theta is 1 at pi over 2. So these are my bounds. So negative pi over 2 until pi over 2. And now I could continue. So I have the integral negative pi over 2 until pi over 2. So on top I have 4 cos theta d theta, and on the bottom I pull out a 2 times, okay, so I'm skipping a step because I pulled out a 2. 1 minus sine squared is cos squared, square root of cos squared is cos. So we've done this before. Disappears. So 2 d theta, so the answer here is just 2 theta evaluated from negative pi over 2 until pi over 2. And that's pretty simple. So it's 2 times pi over 2 minus pi over 2, so I get 2 pi. Any questions?
So please, could you explain how before going to 2?
I'm sorry, how what?
4 over 4 minus x squared going to 2 over 4 minus x squared down to your left. Yeah.
This?
Yes. Yeah.
Oh, because I did the square roots of this. Right? My formula tells me to do the square root of that. So I did the square root of this.
Okay.
Square root of 4 is 2, and the square root of the bottom here is.
Okay.
Okay? Now, what you just did, just for you to see, it's very nice to see it geometrically. Okay, so from -2 until 2. So this is this function here. Okay, by the way, this is y equals square root 4 minus x2. If you square both sides, you get y2 is 4 minus x2. Put the x2 on the left. x2 plus y2 equals 4, with, of course, y is positive because it's a square root. So, you know what the equation of that is? x2 plus y2 equals 4. You know what that is? That's a circle with center at the origin and a radius of 2. Okay, so basically what I did is I found the length of the circle centered at the origin with a radius of 2, but just with the positive y, so it's the top semicircle. So I just found the arc length of this semicircle. So geometrically, right, the circumference of a circle is 2 pi r. So this would be 2 pi times radius over 2, because it's a semicircle and you get 2 pi. That's why it's 2 pi. Okay, that's good to see. It's always good to see it geometrically. So proof of the formula. So here's the situation. I have my curve from A till E. And what I'm going to do is I'm going to do exactly the same process as finding the area under the curve using Riemann sums. Okay, so I'm going to separate into small pieces, n of them. So x1, x2, dot, 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 then xi, and the one before that is xi minus 1, all the way until xn, xo. Okay? But this time, instead of finding the area under the curve, I'm going to find the length of this curve here at that point. So right here and right here. So I have a little length here. Okay, so I'm basically cutting it, the function, into little pieces, and I'm putting length, 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 dot, dot, right, and so on, and so on. Right? You understand what I'm doing? I'm doing all these little lengths, and I'm going to add them all. So first thing, what is this point here? And then what is this point here? Can you tell me?
F of xi minus 1.
Exactly, so it's xi minus 1 and f of xi minus 1. Sorry. That's the point here. And this point here will be xi and f of xi. Okay. And now I'm going to find this length. I'm going to call this length Li, length I. Okay, so the ith length, the first length, second length, third length, and so on until the nth length. And I'm going to add all these lengths. Okay, so basically my length is approximately equal to, to all these little lengths. Okay, so let me just put them here. L1, L2, Li, this is Ln. So L1 plus L2 plus L3 plus. Eventually there's an Li plus dot plus all the way until Ln. Any questions? That's the idea. Okay, that's the approximation, and obviously I'm going to make my n much very big, just like a Riemann sum, and these lengths will be very small, but I'm going to add a lot of them until it becomes almost smooth. So what's Li? You remember the formula, the distance formula? How do you find the distance between 2 points? So x1, x2 minus x1 squared. So xi minus 1 squared plus y2 minus y1 squared. Remember this? F of xi minus f of xi minus 1 squared. And the square root of this. This is the big distance formula. Any questions? Okay. Let's keep going a little bit. I'm going to fix this a bit. Okay. This here, xi minus 1, I'm going to call this, of course, a delta x, right? Just like in Riemann sums. So what do I have here? Square root of xi minus 1, this is delta x squared plus f of xi minus f of xi minus 1 squared. You prove this? And what I'm going to do here is I'm going to extract an delta x squared. So I'm really going to do all the steps here. Delta x squared times 1 plus f of xi minus f of xi minus 1 squared over delta x squared. Do you understand this step? Okay, if I multiply delta x squared times 1, I get this guy. And if I multiply delta x squared times this here, the delta x squared will cancel. I'll be back with this guy. Equals.
Sir?
Yeah.
Please, could you re-explain again why we use the distance between 2 points to find our I?
Why or how?
Why?
Because I'm looking for, remember, my goal is to find the length of this curve, right? I'm trying to find the length of the curve. So I'm going to cut the curve into small pieces and find all these little lengths and add them.
Okay.
Just like I did with the Riemann sum. I wanted the area under the curve. and I separated the area into small little rectangles, and I added the areas of rectangles. Same thing. Instead of adding areas, small areas, I'm going to add small lengths. That's the idea. Is that okay?
Sir,
Yeah.
can you re-explain the last part? I'm not sure.
Sorry.
Can you re-explain the last part, like the last line you wrote?
This part here.
Yeah.
Okay. So before you're okay,
Yes.
the last part here, the only thing I did is I factored out a delta x squared. I factor it out. Okay. So look, if you multiply delta x squared times 1, you get delta x squared. And if you multiply delta x squared by this expression, right, the delta x squared will cancel, and you'll be back to this.
Okay. Why don't we do like delta fx?
Delta fx
Yeah.
here on top.
Yeah.
You could. I don't know why you want to do this. I'm trying to recognize a Riemann sum here. Okay, so let's continue. I'm going to now apply the square root of delta x of delta x squared, so it becomes just delta x. So I have now what? Square root of 1 plus, and here I will have f of xi minus f of xi minus 1 over delta x, all this squared. I should have done it a bit. I'm going to do it a bit lower because I have no space. So equals to square root. There you go. 1 plus, and I'm going to have f of xi minus f of xi minus 1 over delta x squared times delta x. Okay, so this is now what I have for Li. So this length is now the sum I equals 1 until n, right? I'm adding all of them of this expression here. Square root 1 plus, so f of xi minus f of xi minus 1 over delta x squared, all this times delta x. Okay, so this is pretty much a Riemann sum. Because the limit will now be equal to, the length will be equal to the limit as n approaches infinity. So exactly equal, not approximately anymore, just like a Riemann sum. N approaches infinity, sum I equals 1 until n, square root 1 plus f xi minus f xi minus 1 over delta x squared times delta x. Okay. Almost done, one step. And so this is equal to the integral from a to b of the square root 1 plus, and this, if n approaches infinity, then delta x approaches 0. This is the exact definition of the derivative, f prime of x squared, and delta x, of course, becomes dx, and the proof is done.